This is SS06, June 2013, question 2. Experimental design used for analysis by analysis of variance. This question has quite a lot of wording to it, but if you summarise it, it's quite easy really. Semiconductor wafers are produced in large batches at a manufacturing facility. These wafers receive doses of an implant material in a diffusion process that takes place in a furnace. Engineers are to investigate whether different material doses, have a significant effect on resistivity measurements. They're going to use 4 different doses of implant material. 12 wafers, all selected from the same batch, 12 wafers obtained. But you can only put 4 wafers in any one furnace run, so the wafers will have to be tested in 3 different furnace runs. Name the blocking factor. Name the treatment factor. I'm going to talk about the treatment factor first of all. The treatment factor is what we're actually looking at investigating. So in this particular case, the investigation, the engineers wish to use 4 different doses of implant material. So the treatment factor is the doses of implant material. The blocking factor is whichever factor is being used to minimise experimental error. In this case, you know all the wafers are from the same batch. You've got different furnace runs. If you've got 3 different furnace runs, then it's important to consider that, because there will be differences between the different furnace runs due to experimental error. So the furnace runs are going to be your blocking factor. Part 3. Give a reason why the 12 wafers should be chosen from the same batch. Clearly, you want to minimise any experimental error. You've got to ensure that your wafers are as identical as possible. That is the reason why you would ensure that all 12 wafers are from the same batch. Here are the written answers that I've just gone through in words. Blocking factor, furnace runs. The treatment factor, what we're looking at, is the doses of implant material, because you've got 4 different doses, so it's the doses of implant material. And a reason why the 12 wafers should be chosen from the same batch. Minimise experimental error, and an explanation. If all the wafers are manufactured in the same way, this would mean they are as similar as possible, which will mean that any differences in what we're trying to measure will be due to implant doses or the furnace runs, the blocking factor. Okay. Part B. One engineer, Eric, suggests using a completely randomised design for this experiment. Another engineer, Harriet, suggests using a randomised block design. Explain why Harriet's suggestion is preferable to Eric's. We have already talked about using the furnace runs as a blocking factor. Now, Harriet's suggestion, using a randomised block design, takes into account the differences due to different furnace runs, which would increase the experimental error if it were not blocked, because of the differences in the furnace runs. Eric's design does not take these runs into consideration. second part of part B asks you to complete table 1 to illustrate Harriet's suggestion for this randomised block design. If these are the different furnace runs, the implant material on the wafers, you have to ensure that the different implant doses are on wafers in each of the 3 runs. So you've got D1, D2, D3, D4, D1, D2, D3, D4. In any order, it doesn't matter which order you put them in, as long as you've got D1 to 4 in each of them. I've seen it shown where you just write implant doses here, D1, D2, D3, D4, and put an arrow showing that you get basically 4 different doses on the 4 wafers in each furnace run. Part C, nice easy 2-mark question. Name the technique that you would use in order to analyse data obtained from an experiment using Harriet's suggested design. You've got 2 factors, so that is going to be a 2-factor or a 2-way analysis of variance, which, if it was an exam, I would write in full analysis of variance. That completes that question.